The journey of life relies heavily on the proportion of carbon dioxide and other gases in the air. The presence of different biomarkers increases the possibility of life existing. Imagine a scenario where abundant life thrives on heme planets, which are worlds roughly 2 to 3 times the size of Earth, covered by a single vast ocean. These heme planets represent a new class of celestial bodies that intrigue scientists and are technically known as subneptunian planets. Heme water worlds captured attention when the James Webb Space Telescope detected significant amounts of water and a hydrogen-rich atmosphere on the exoplanet K2-18b. This discovery suggests the potential presence of a large ocean and, possibly, life. K2-18b, an exoplanet with 6 to 8 times the mass of Earth, orbits the cool dwarf star K2-18 within the habitable zone, approximately 120 light-years from Earth. The size lies between that of Earth and Neptune. The presence of methane and carbon dioxide, combined with the absence of ammonia, supports the hypothesis that K2-18b may harbor a water ocean beneath its hydrogen-rich atmosphere. James Webb also identified another intriguing molecule, dimethyl sulfide, DMS. On Earth, DMS is exclusively produced by life, primarily by phytoplankton in marine environments. Upcoming observations by Webb are expected to confirm these findings, potentially providing significant evidence of biological life on K2-18b. This life could range from simple forms like microscopic algae and microorganisms to more complex organisms, such as fish or aquatic mammals. The possibility exists that life forms on other planets might exceed our current imagination. Even on a planet entirely covered by water, higher life forms could have adapted to living in aquatic conditions. The presence or absence of landmasses on K2-18b remains uncertain and challenging to determine from a distance. Adding to this intriguing scenario is James Webb's ability to detect artificial light emissions, such as those from cities on distant planets. This capability represents a significant advancement in our search for extraterrestrial life. It is important to note that K2-18b was not initially discovered by James Webb. Rather, the Hubble Space Telescope provided the first insights into its atmospheric properties. The promising data from Hubble led researchers to revisit their studies with the new telescope, resulting in rewarding discoveries about K2-18b. These studies are captivating and could mark our first identification of signs of life in space. This discovery is groundbreaking, considering the nearly century-long search for life within our solar system, which has yielded no definitive results. So far, no living organisms have been found in our planetary system, with only the distant, icy moons orbiting Jupiter and Saturn being considered potential candidates, according to scientists. High-end exoplanets could be genuine super-Earths and possible cradles of diverse life. Life on Earth began in water, with the emergence of landmasses and mammals occurring later. If Earth had remained a water planet, intelligent life forms adapted to an aquatic existence could have evolved. Traditionally, the search for extraterrestrial life has focused on exoplanets resembling Earth, particularly smaller rocky planets. However, larger heme planets are now being considered the true super-Earths in the cosmic realm. While not all experts share this optimism, there is a possibility that the oceans on these planets might be too hot to support habitable or liquid conditions. In such cases, heme worlds could resemble titanic steam baths. Nevertheless, the presence of life in the hot and toxic thermal pools of Yellowstone National Park demonstrates life's resilience, even in extreme conditions. The exploration of K2-18b raises a compelling question. Can we ever truly determine whether the exoplanet is inhabited? If intelligent life were found in space, the natural inclination would be to establish contact. However, K2-18b, located around 124 light-years from Earth, presents a significant challenge for our current space travel capabilities. It takes years for our probes to reach destinations millions or billions of kilometers away. A planet 124 light-years away, or even one just 4 light-years away, remains beyond our practical reach with existing probes or spacecraft. The Voyager probes, launched in the 1970s, will take several thousand years to reach the nearest star systems. Communicating with species in the universe would require innovative approaches. Discovering Earth-like planets in nearby star systems, such as Proxima Centauri, inspired space enthusiast Yuri Milner to design nanoships. These tiny probes, equipped with cameras, are expected to cover several trillion kilometers in just a few years, capturing images of planets that could harbor life. If a civilization in space were detected, researchers would likely develop entirely new strategies. Such ambitious goals fuel our spirit of exploration and innovation. In a theoretical future, with warp drive technology enabling travel through the universe by folding spacetime, journeying to worlds like K2-18b would no longer be a challenge. However, our current space transportation operates within the constraints of Newtonian physics and relies on propulsion through forces and momentum. Even if a spaceship capable of traveling at 10% of the speed of light were built, the journey to K2-18b would still take 1,240 years. A radio transmission traveling at the speed of light would require 124 years to cover the distance between Earth and this distant exoplanet, and a response would arrive an additional 124 years later. The study of exoplanets, exemplified by K2-18b, demonstrates that the search for extraterrestrial life has long been a fundamental pursuit in astronomy and astrobiology. As technological advancements continue to evolve, our ability to detect and explore distant worlds has significantly improved. One of the most exciting discoveries in recent years is the exoplanet K2-18b, located approximately 120 light-years from Earth. This planet has become a focal point for researchers due to its unique characteristics that suggest the potential for habitability and possibly even life. This extended exploration will delve deeper into the scientific context of K2-18b, the advancements involved in its study, and the broader implications for our understanding of life beyond Earth. The significance of K2-18b. K2-18b is an exoplanet situated in the habitable zone of its host star, a cool dwarf star known as K2-18. This zone is critical because it is the region around a star where conditions may be suitable for liquid water to exist, a key factor for life as we understand. K2-18b's size falls between that of Earth and Neptune, making it an excellent candidate for studying atmospheric and geological characteristics that could indicate habitability. Atmospheric composition. One of the most compelling aspects of K2-18b is its atmospheric composition. Observations from the James Webb Space Telescope, JWST, revealed a hydrogen-rich atmosphere with traces of water vapor. The detection of water vapor is significant because it suggests the presence of a substantial amount of water, possibly in the form of a vast ocean. The presence of methane and carbon dioxide further supports the hypothesis that K2-18b could have a greenhouse effect, which could contribute to maintaining stable temperatures conducive to liquid water. Methane is particularly interesting because, on Earth, it is primarily produced by biological processes. Its presence, along with other gases, helps build a profile of K2-18b's atmospheric chemistry and could offer clues about potential biological activity. The absence of ammonia, a common toxic compound, is also notable, as it supports the idea that the atmosphere could be more hospitable. Technological innovations. The discovery of K2-18b has been made possible by advancements in space telescopes and observational technology. The James Webb Space Telescope, in particular, has provided unprecedented detail in its observations of distant exoplanets. Its ability to detect and analyze light from distant worlds has revolutionized our understanding of exoplanet atmospheres. The JWST is the most advanced space telescope ever built and represents a significant leap forward from its predecessors, like the Hubble Space Telescope. Equipped with powerful infrared instruments, the JWST can peer through the thick clouds of gas and dust that often surround exoplanets and their host stars. This capability allows scientists to explore the atmospheric composition of exoplanets in extraordinary detail. The telescope's ability to detect dimethyl sulfide, DMS, is especially important. On Earth, DMS is a molecule produced exclusively by life forms, primarily phytoplankton, in marine environments. The presence of DMS in K2-18b's atmosphere could be a strong indicator of biological processes, suggesting that life might exist on this distant world. The search for extraterrestrial life. The search for extraterrestrial life encompasses a variety of approaches, from examining exoplanet atmospheres to searching for signals from advanced civilizations. The discovery of potentially habitable exoplanets like K2-18b is a crucial step in this search. Biomarkers are substances or molecules that indicate the presence of life. In the context of exoplanet research, identifying biomarkers in a planet's atmosphere can provide evidence of biological activity. The presence of gases like methane and oxygen, particularly in combination, can be a strong indicator of life. On Earth, these gases are produced by living organisms, and their detection on other planets could suggest similar processes. The Drake equation is a tool used to estimate the number of active, communicative extraterrestrial civilizations in the Milky Way galaxy. It considers various factors, including the rate of star formation, the fraction of those stars with planets, and the number of planets that could support life. The discovery of potentially habitable exoplanets like K2-18b adds valuable data to the equation, helping to refine our estimates and guide future searches. Challenges and future prospects. Despite the exciting discoveries, the study of exoplanets like K2-18b presents several challenges. The vast distances involved and the limitations of current technology make it difficult to gather direct evidence of life. Distance and travel limitations. K2-18b is located 120 light-years from Earth, a distance that presents significant challenges for space travel with current technology. It takes years for spacecraft to reach even the nearest star systems, and traveling to a planet 120 light-years away would take thousands of years with current propulsion systems. Radio signals, which travel at the speed of light, would take 120 years to reach K2-18b and another 120 years for a response to return. This long communication delay makes it difficult to establish contact with any potential civilizations on distant exoplanets. The need for advanced propulsion systems. To overcome the challenges of interstellar travel, scientists and engineers are exploring new propulsion technologies. One concept is the idea of warp drive, which would allow spacecraft to travel faster than the speed of light by bending or warping spacetime around them. However, this concept remains purely theoretical, and practical implementation is far from being realized. In the meantime, smaller, more feasible technologies like light sail probes are being developed. These tiny probes could be propelled by lasers or sunlight, reaching a fraction of the speed of light and potentially traveling to nearby star systems within a human lifetime. The role of AI and machine learning. Artificial intelligence, AI, and machine learning are playing an increasingly important role in the search for extraterrestrial life. These technologies are used to analyze vast amounts of data collected by telescopes like the JWST, identifying patterns and anomalies that could indicate the presence of life. AI can also help optimize the search for extraterrestrial signals, sifting through radio waves and other forms of communication for signs of intelligent life. Future missions and technologies. Future space missions and technologies will continue to advance our understanding of exoplanets and the potential for life beyond Earth. The European Space Agency's Ariel mission, set to launch in 2029, will focus on studying the atmospheres of exoplanets, including their chemical composition, temperature, and cloud structures. The planned LUVOIR, Large UV/Optical/IR Surveyor telescope, if developed, will be capable of directly imaging exoplanets and searching for signs of life on their surfaces. Philosophical and ethical considerations. The discovery of life on other planets raises profound philosophical and ethical questions. How would humanity react to the discovery of extraterrestrial life, particularly if it were intelligent? What rights and responsibilities would we have in interacting with other life forms? These questions have been explored in science fiction for decades, but they may soon become a reality. The search for life on exoplanets like K2-18b is more than just a scientific endeavor. It is a journey that challenges our understanding of our place in the universe. As we continue to explore distant worlds and push the boundaries of our knowledge, we may one day discover that we are not alone in the SOSM.